started, and remember first of all that what we were looking at. So we were looking at these sets that were productive and creative, and the idea of productive sets was that a set is productive if you can distinguish this set from any computably enumerable set contained in it in some sort of effective way. So if you get an index of a set which is contained in P, then psi of x is in P minus wx, and psi of x was some partial computable function, and creative was just a complement of productive, not quite, and computably enumerable. We care about all sets of natural numbers, but just a little bit more about the computably enumerable sets, and this way we get some nice theorems. What did we notice? K bar was productive as shown by the identity function, and we noticed that this function, right, the definition says that this is just some partial computable function, but then we discussed a theorem which showed that really it can be assumed to be 1-1 total and computable. So a given production function can be spruced up a little bit to be better. So I guess you might as well have put this in the definition, except that the theorem that shows this has these two nice ideas of how do you say, massage the function into something nicer, and so it's a nice theorem that way. Okay, so with this, we can make some nice observations. Theorem. If P is productive, then P is not CE. Kicking in an open door, if I ever saw one. If it is productive, then it is also the case that P contains infinite CE sets. So you're not productive because you just don't contain any WX. You're productive for this statement here is not a vacuous statement for a productive set. There are such CE sets contained in it. And so then we need to, right? How do you show it contains an infinite CE set? Well, you need to construct one. And the way to construct one is to realize that, well, but it always contains, every set contains CE sets, because the empty set is CE. So you always have an empty set to start with, and then you can take the index of this empty set, and then if you compute psi on the index of this empty set, you know it converges. Well, I guess we know it always converges, but you already knew it converges. So then you get one element in P. Now you have this one element in P. The CE set, which consists of just singleton this one element, is a subset of P, and you can easily obtain an index for it. And then if you put that index into P, then you get a different element of P. Then you have two elements of P. These two elements of P can be put into a nice CE set, for which again you can easily obtain an index. And you apply psi to that index, and you get a third element of P. And so what I just described Right? And whenever I said in this little story there exists an index, what I should have said is there is a uniform strategy of from the input information effectively obtain that index. And so I just described how to, by iterating this strategy, come up with a function whose whole infinite range is contained in P, and it's a 1-1 function. And if you have a computable 1-to-1 function, its range is a CE set, and it is this infinite CE set that's contained in P. Also, if P is productive, maybe I should move over a few more spacious next board.
Is the reason you can effectively get an index for these sets, these CE sets, because they're finite? Is that?
Yes.
Okay.
So they're finite, and you have already obtained, you have in your hands these finite things, right? If you just knew it was finite, but you didn't have the elements in hand, then you still couldn't quite get that. But because you know it's finite, you have computed one element after the other, so you have an explicit listing of all the elements, and then you can easily obtain an index. So also, still, if P is productive, and P many one reduces to A, then A is productive, or I guess productivity is infectious under many one reducibility. So given a production function for P, using the many one reduction, you should be able to transform it into a production function for A. Well, I guess that says a little bit more than what the theorem says, but that's how you prove it anyway. So what we want to see is whenever you have Wx a subset of A, then we need to find, let's call it psi A of x in A minus Wx, and we can already do such things for P. Now, how do we do this? Well, let's call this reduction here f. So we have the reduction function f, and we have the reduction function f. What does this reduction function do? Well, anything inside of P maps inside of A, and anything not inside of P maps not inside of A. So from this here, we get exactly that the f inverse of Wx is a subset of P, because Wx, all the elements in there are in A, therefore under the inverse, all the elements end up in P. But this now is pretty nice, because this, of course, right, given this x and this computable function f, you can effectively obtain an index for this set. Let's call this what do I care? Wg of x. Right? If I have a computably enumerable set and I have inverse like this, then I obtain the CE set, and I can effectively find this index for the CE set. But this now is nice, because then we know that psi of g of x is in P minus W g of x. Right? And of course, I'm only looking at this sequence of implications under this original assumption, also because I just don't have to care what my production function does if this assumption is not the case. So I only worry about this. So now what do I have? I have something in P which is not in Wg of x. Well, Wg of x exactly consists of those things which map into Wx, but it's still in P, therefore the function f still maps it into A, So this means that f of psi of g of x is in a minus wx, which shows that this function f psi g is a production function for the set A, and so indeed productivity is infectious as well. Oh, I guess I should say. Good. So productive means you're not CE, you contain an infinite CE set, and it goes around like that. But it turns out things are even slightly better than that. And that is that we have one example of a productive set. And productivity is infectious like this. And so it turns out that anything which is productive because of these two reasons combined. That is to say that if P is productive, this happens if and only if K bar, well, even 1 reduces to P. The right to left is of course the theorem we just proved. It's K bar is productive. If it 1 reduces, then it many 1 reduces, therefore then P is productive. So we only need to show the left to right one, and then the left to right one shows exactly that productivity follows because this particular productive set reduces to U. And with this, we also observe that creative is the same as being 1 complete, because we know that K bar is 1 complete, and we know that K is 1 complete, the complement, which nicely fits. And so complement of creative exactly means that K bar reduces to U. K bar reduces to U exactly means you're creative. And I said it wrong again. K reduces to U exactly means that you're creative. And so that is to say this, the first equivalence implies the second equivalence, so we only have to show the first equivalence. And to show the first equivalence, we just show that if you're productive, K bar reduces to U in a nice way. So we need to come up with a nice reduction. And this is how we do it. Right, we assume little p is a 1-1 total computable production function for p. It has a production function, therefore it has a nice production function. Then using this, you can define W of fxy to be singleton P of x if y is k, empty set. Otherwise, and again, by now it's starting to become, I hope, a Pavlov reaction. You see case distinction. The case distinction is not computable. Right? Y and k is not computable, but that's okay because the other case is empty. So the case distinction is exactly right. You start computing whether y, whether if you take Turing machine y, start run it on input y, you just start running it. If you never stop, you already found an index for an empty set. If you ever stop, then you check your input and see if it's equal to p of x. You aren't given p of x, but p is a total computable 1-1 function, therefore you can quickly compute p of x, compare your input to p of x. If it's equal, you stop. If it's not equal, you go into a silly infinite loop. And that's exactly what f of xy does. Having this, we can use the recursion theorem to get a 1-1 computable function ny such that w of ny is equal to w of f of ny y is equal to p of ny if y is in k empty otherwise. The last thing is just rewriting the definition. So of course you're going to look at this and say, well, that's not how I remembered you talking about the recursion theorem before, but this is the recursion theorem with parameters, right? Recursion theorem before was for functions fx with just one parameter, and then we managed to find this so-called fixed point. But we observed that in finding this so-called fixed point, that finding this point was really effective. You, from the function and everything else, you could effectively find this fixed point. In particular, you can effectively find it still in the presence of a parameter. But then what the value is of the fixed point, of course, differs from one parameter to the other parameter. And that's why you get a function which depends on the parameter. You don't just need one parameter. However many parameters you like, you can put in there. The exact same proof of the recursion theorem works out. Well, notation is different, right? But how do you say mutatis mutandi? Does that mean what I think? Right?
What does that mean?
Change the obvious locations. Look at the proof, change it in the obvious ways in which it clearly needs to be changed, and then it all works. I don't know enough Latin to actually know the translation. Somebody use it?
Well, the mutatis is the changing.
With the
But mutandi sounds like changing too.
with the changes made or something. With the necessary changes made or something like that.
But that's what it means. If mutatis mutandi does not mean that, then change mutatis mutandi to with the necessary changes made. Anyway, if you look at the proof, and by now you've had this proof long enough, and I told you that's important, and you should spend time with it. So you sit back and you think for a moment, and you say, yeah, I can see that, and then it's all good. So then we're nearly there, because we needed a 1-1 reduction function, and now we have a 1-1 computable function. And this is the reduction function, so now we just need to see that. So if y is in k, then w ny is equal to p of ny, right? It's singleton. And now you notice, right? Here it looks like I was just randomly playing around with these functions, which maybe I was at that time, but here you can see what happens, because now, what do you notice? Well, what you notice is w of ny could not be a subset of p, because if it was a subset of p, then p of the index should be in p, but not in w of ny. the one thing that's in this subset is P of its index, right? That's the typical recursion theorem kind of thing, that you can define a set in terms of its index itself, and here we made it so that this W of ny exactly contains the one thing which it shouldn't contain. Therefore, we get that P of ny is not in P, which is the same as P of ny is in P component. And that's exactly what we wanted, right? If you're not in K, then you should be in P. So if you are in K, you should be in P component. So that's half of the statement. The other half is the next implication. If y is in K bar, then W of ny is the empty set. Well, and the empty set, nicely enough, is in fact the subset of P, and therefore P of ny is in P. Well, according to the definition, it's in P minus the empty set, which is exactly to be in P. And so these two sequences of implications show that this ny, as obtained by the recursion theorem, is indeed a 1-1 reduction. Right, and again, the 1-1ness didn't seem to play a big role in the proof of the recursion theorem, and it didn't, but it was easy to obtain by
Adding strings.
adding dummy instructions, right? So the 1-1ness, whether you had it or not, you can always achieve it, because we're just talking about indices. That's that. And so what does that give us? Indeed, that creativeness and one completeness is the same, and I guess it's really the case that this shows that creative, M-complete, and one complete are all the same. I'm not claiming that all M reductions are 1 reductions, or all 1 reductions are M reductions, or that they can be made like that. But for this one specific degree that we're looking at, they do correspond. It's kind of nice. I think factorization. It would have been nicer if in there was Turing complete, but it isn't. So in that sense, if you really take what we started with in this course serious, that what we cared about is the structure of the Turing degrees, then this here was a failed attempt at characterizing Turing completeness. But it's nice anyway.
Why are you characterizing this as a failed attempt? I mean, what?
Oh, because I'm complete, one complete, but right.
Right.
And I'm not. It's not a failed attempt in many ways at all, because it's creative sets are an interesting collection of sets, and it turns out they characterize some really nice notions. They do not characterize Turing completeness.
Okay, so I mean, there's no impediment to characterizing Turing completeness. This isn't the way to do it.
Yeah.
Okay.
So in that sense, right? things would have been nice if in this list it included Turing completeness. It doesn't, and only as far as that goes is it a failed attempt. Otherwise, I'd say it's a pretty nice attempt because I think the arguments are pretty nice. We're mathematicians, what do we care about? As long as the arguments are nice, then you have something nice going on. Okay, so the next thing I want to do is to do a first construction where we have a set of requirements to satisfy. In the end, like we're going towards priority arguments, and then you have a set of requirements and lots of administrative stuff on top of that to make things work out. But here is a kind of simpler version. So this theorem is called the Friedberg splitting theorem. And what the Friedberg splitting theorem says is that if you have B computably enumerable, not computable, then you can split B into two parts with those same properties. So let's just say, then there exists A0 and A1 computably enumerable such that B is equal to A0, and disjoint. Without the disjointness, it's quite easy. B is equal to the union, and A0 and A1 are already said CE, not computable. But let me check that I got all requirements, because that looks about right. So if you leave out any of these requirements, you suddenly have a trivial problem where you can choose either A1 and A0 both equal to B, or you can choose A0, a finite subset of B, and A1, B minus that finite subset. But with all of these together, something really is happening. You have your set B, it's complicated, therefore it's written by a perfectly regular kind of object, and you can cut it in two, and now you have two parts, both still computably enumerable, but also both not computable. So a fair bit of the ideas that go into this proof are going to be elaborated on in our later proofs and used to prove much more interesting kind of statements. But it's nice to start thinking about this already. And so, what's the basic outline? Oh, right. So constructing two sets which are computably enumerable. Of course, one way would be, given an index for B, let's call it little b, so we can say B is equal to W of little bit. Given this index for B, we somehow need to come up with indices for A0 and A1, and we could imagine major creativity and just, there they are. Not usually the way you do it. So how can you do a construction that results in computably enumerable sets? That's sort of basic question number one that you want to ask in this kind of context. We need to construct two computably enumerable sets. how at all do you construct a computably enumerable set? Well, the usual strategy for this is that you come up with a strategy which proceeds in stages or something like that, and you just keep going, you keep chugging along, doing stuff. Now, if you do stuff that's not computable, then you should have no hope of getting computably enumerable sets out of it. So what you want to do is come up with a strategy where you keep doing computable stuff, and while you're doing these computable stuff, like you compute to test whether this is true, you compute to test something else, you compute this, and then along the way, every now and then you say, and now I enumerate this thing into A naught. And then a little while later you keep computing, and then you say, and now I enumerate this thing into A1. And you keep on computing a little bit. And if you look at this description, you can easily extract from it a function which enumerates A naught. You just keep on chugging along and you ignore whenever the other set gets enumerated in. But you can also easily obtain a function which enumerates A1. And so this is the basic strategy for constructing computably enumerable sets. You write down a description of your construction of these two sets, and the description is do lots of computable stuff, every now and then say, put this in A naught, put that in A1. If you can do that, then you get computably enumerable sets. So that's nice. We have a strategy for one of our requirements. The strategy for the disjointness, just don't be stupid and enumerate something in both A naught and A1. Right? You were there while you were enumerating. Yeah, make sure you don't enumerate into both of them, and it works out. The strategy for this, B should be equal to A naught and A1. Well, that's no big problem either, because B is a computably enumerable set. So in particular, we have, it's not computable, so it's infinite as well. Right? Finite sets are computable, therefore this is an infinite computably enumerable set. Therefore, we have a computable 1-1 function which enumerates the elements of B. So in particular, in our going around doing lots of computable stuff, we can, whenever we please, ask, give me the next element of B. And then we compute this function and we get it. And so now we combine these two strategies. Every now and then in the strategy, we will say, give me the next element of B. And then I look at this next element, I check some things about it computably, and depending on the answers to these computable checks, I put this element of B into A naught or into A1. And so if I keep on doing this, for whenever I want an element, I generate the next element of B and then I put it into A naught and A1, I get this equation. So now we have strategies for everything except for making A naught and A1 not computable. Well, so I'm now gonna, I think maybe, I'm not quite certain, complete a large part of the proof of this thing, but there will be one important gap left over, and this important gap is then what we'll finish on Wednesday. There's no way I can fit all of that in there. So this is, everything is kind of clear except for the non-computable part. So how am I going to achieve non-computable? Well, I am already constructing them, as you can clearly see. I am already constructing these things as computably enumerable sets, right? As soon as it appears there, it should be following this thread. So to make them not computable, the right thing to achieve is to make sure that their complements are not computably enumerable. Computable means it and complement computable. What did I say? Computable is equivalent to it and its complement being computably enumerable. I make them computably enumerable, so not computable means the complement is not CE. Well, when you write this down, I'm not giving you a strategy yet, all I'm saying is, okay, so then I can write down a requirement that says that WE is not equal to AI complement. Right? And I have this requirement for all values of E and all values of I. Well, there's two values of I, 0 and 1. If I can satisfy all of these requirements while doing all the other stuff I described here, we win. Right? I've just taken the last requirement for which we didn't know what to do yet, and I've written down its requirements. Or the last property, I should say, to use the last property we didn't yet know how to deal with, and now I've written down a set of requirements to satisfy it. So what that buys you is that the property you want, which is one very complicated property, has now been separated out into infinitely many but easier properties. Okay. And now we can look at one of these properties and imagine how would you satisfy such a property? Well, of course, one way you might satisfy such a property is that it's just accidentally already satisfied. This is always possible, and it means you don't have to do anything. But then there are the cases where it's not. Then there are the cases where it's not automatically satisfied, and we need to come up with a strategy. So what is the strategy? I want to make AI complement different from WE, and I would like to do it in a way that once I've done it, I'm done with it. You can't always do that. This is exactly where the injury comes in. Injury of requirements is defined essentially as you've done work to satisfy a requirement, and then later you do work which injures the requirements, which means that it undoes the work you did before. But these requirements, we can come up with a strategy that once you act on a requirement, you explicitly make it satisfied, it's forever taken care of, which is very convenient. So what do we do? Well, what you would like to see is you're going along, you're enumerating these elements of B, and at some point you observe an element which is both in B and in WE. And once you have an element which is both in B and in WE, then you can stick it into AI, and then you have forever satisfied this requirement. But it's very important in my description of how I construct these things to be CE. I said every now and then you say, and now I put this in A0, and now I put this in A1. Never ever will you take something out of A0 or out of A1, because then you completely ruin its computable enumerability in principle. So that's what we want. Find something which is in both B and in WE. And that's exactly what we're going to do. So now I can, oops, now I can describe the construction. Let me just describe the construction, and then maybe we'll just look at its properties next time. So like I said, it goes in stages. At stage 0, the first stage, what we do, where did it go? We just take F0 and put it into A. F0 is the function which enumerates B, or F is the function which enumerates B, and so this says, take the first thing that we enumerate into B and put it into A0, just to get started somewhere. Then at stage s plus 1, what do? Well, we have here these infinitely many requirements, and at any stage, many of them look like they're not satisfied, but we need to pick one. So we say, look at the least pair EI, if it exists, maybe it doesn't exist yet at this stage. Look at the least pair EI, such that at this point in time it looks like R of EI is not satisfied. Now you should have observed that, of course, checking whether there is something in B and in WE is problematic, because both of these are CE sets, and for the one we have a nice enumeration, but right, if you have two enumerations like this, it might take forever until you find a joint element, and you never know when it's not going to happen, so you need to work with some approximations, and that's exactly what we do. We enumerate the next element of B, right? Stage S plus 1, or I guess at stage S, the S element of B gets decided where it goes. So now we need to decide where does Fs plus 1 go, and like I described before, to decide where Fs plus 1 goes, you need to do something computable. Well, what's the best thing I can do? The best thing I can do is check whether this is in WE. I can't do that, but I can check if it's in WE by stage S. Now, part of explaining how this works is being a little bit more careful, or sort of giving a redefinition of this, but the intuition that it is in WE and S tabs is the right one. So this certainly is a computable requirement. If this happens, and it is the case that WES intersect AIS is empty. So this is exactly, if you look at it, this is exactly, does it look like REI is not yet satisfied with everything we can compute up to this point? If that's what it looks like, then we want to put Fs plus 1 into AI. Then Fs plus 1 goes into AI. So we look at the least requirement where it currently looks like it's not satisfied, and we act on it. And now time's up. But the thing is, this works. And now you have very good reason to be doubtful about this, because there is something very confusing about orders of enumerations that goes into this. You can easily imagine that the order of enumeration is such that these elements eventually always enter into WE, but they always enter just too late, in such a way that you don't get to them in time for this computable requirement to take care of them. And so this is going to be the big trick on Wednesday. Wednesday, right? Yes. The big trick on Wednesday, that even though it looks like this could always be computed too slowly, it turns out there's good reasons that it's not. And that the timing, in fact, sufficiently often works out in our favor that this really is the construction. And then you notice that once we do that, we can easily see that we can check that all these requirements are satisfied, and all the other properties here are clearly automatically satisfied by the other story I gave.